Looking at this simulation of a metallic beam under load, we see a core challenge in solid mechanics. Continuous physical systems deform in infinite ways. They are governed by differential equations that often lack an exact analytical solution. To bridge this gap, engineers rely on weighted residual methods. Instead of hunting for an impossible perfect answer, we build mathematical approximations designed to minimize the total error, or residual, across the system. Within this family of techniques is a highly efficient approach known as the collocation method. This plot shows how it works. Rather than calculating error across the entire continuous domain, this method forces the residual to be exactly zero at predetermined discrete coordinates. We are trading the requirement for global accuracy for the ability to force the approximation to be exact at specific coordinates. Think of this discrete constraint physically, like aligning the two open edges of a shirt. If those edges have no connections, they move independently. In our math, that gap represents a massive error between the approximation and reality. Applying a single constraint forces the sides to meet at one exact coordinate. Space between still wiggles, leaving residual error. Increasing constraint points shrinks deviations. At the infinite mathematical limit, like closing a zipper, the approximation converges perfectly into the exact continuous solution. Mapping this physical analogy back to the math, those buttons are our collocation points. We denote them as internal coordinates, xj. By strategically placing a finite number of these constraint points, we collapse the infinite complexity of continuous mechanics into solvable finite algebra. To see how this generates an actual matrix, let's take this geometric intuition and apply it to a classic solid mechanics scenario. Here we have a one-dimensional structural bar. The left side is fixed rigidly to a wall at coordinate x equals 0, and the right side is completely free at coordinate x equals L. We apply an external excitation in the form of a distributed force, f of x, pushing across the entire length of the material. This equation describes the continuous physical state of the system, the material stiffness constant, EA, multiplied by the second derivative of displacement, plus our external force equals 0. Before we solve anything, we have to define the absolute limits. At the fixed wall, the physical constraint means the displacement, u, must be exactly 0. At the free end, there is no opposing force. Therefore, the strain and the mathematical slope of the function, u prime, must also be exactly 0. These boundary constraints form a rigid border. Any mathematical approximation we build must flawlessly respect these limits before we even consider evaluating the internal points. We construct our mathematical approximation, the trial function u of x, by summing individual chosen functions, denoted as psi I, each multiplied by an unknown coefficient, ai. We cannot plug just any random equation into this summation. The functions we choose have to pass strict admissibility conditions. First, these trial functions must inherently satisfy the border constraints we just established, 0 displacement at the wall and 0 slope at the free end. Because our selected functions handle the borders, our collocation points, the xj coordinates, are only placed internally within the domain. Second, the trial functions must be sufficiently differentiable to survive being plugged into the governing equation.
If we try to use a simple linear function, like ax plus b, we hit an immediate dead end. The governing equation for our bar requires a second derivative. Differentiating a linear function twice yields 0, mathematically wiping out the entire system. To get a non-zero result, we must choose quadratic, cubic, or higher-order functions to act as our valid trial functions. With admissible functions selected, how do we force this trial function to have 0 residual error at specific internal points? Mathematically, evaluating at a specific point is modeled by selecting a weighting function. By choosing the Dirac delta function, which spikes infinitely at a single point, we create a filter that plucks the value at coordinate xj while ignoring the rest of the domain. Strict boundary admissibility ensures our function fits the physical space. Dirac delta weighting lets us sample the continuous differential equation at precise, discrete coordinates. Now we combine these pieces by substituting our admissible trial function summation directly into the governing equation of the 1D bar. As we assemble the equation, the material constant EA and the derivative operator pass cleanly inside the summation symbol. Notice that the derivative acts exclusively on our chosen known trial functions, psi I. The unknown coefficients, ai, remain completely untouched. Next, we apply the collocation principle. We evaluate this entire continuous summation precisely at one of our chosen internal points, xj. By evaluating at a specific coordinate, we collapse the continuous function into a single algebraic equation. If we select a total of n internal points, this single evaluation step scales. It generates a vertical stack of n discrete algebraic equations. This stack is exactly what we need. We now have n equations perfectly aligned to solve for our n unknown coefficients. At this stage, we have successfully crossed over from the complex, continuous realm of differential calculus into the highly programmable realm of discrete linear algebra. We organize this stack of algebraic equations into standard structural matrix form, yielding a stiffness matrix K, a coefficient vector A, and a force vector F. If we look inside the newly generated stiffness matrix, we see how the geometry maps to the math. A single matrix entry, Kij, is explicitly defined as the constant Ea multiplied by the second derivative of the trial function evaluated at the specific point. Index I tracks trial functions across columns, and index j tracks spatial collocation points down rows. This formulation reveals a critical trait. Unlike standard finite element matrices, mirroring cells across the diagonal are not equal. The resulting stiffness matrix is generally asymmetric. The resulting asymmetry stems from the specific points we've sampled and the inherently non-symmetrical physical conditions at the bar's fixed and free ends. We began with a continuous physical structure governed by an equation with infinite possible deformations and forced it into a solvable, programmable grid. This relies entirely on two pillars: mathematically admissible trial functions acting as the continuous fabric, and strategically placed internal points acting as the binding constraints. By forcing the residual error to zero at specific coordinates, the collocation method provides a rigorous pathway from physical structural intuition to rapid computational execution.